Kem cho, future engineers. Look at this scale. When you step on it and the dial lands on 70 kilograms, most people would say that's your weight. But if we want to understand how structures actually work, we have to look closer at what that number really represents. That 70 kilograms represents your mass. Think of mass as the actual physical stuff, the atoms and molecules that make up your body. We measure that amount of matter in kilograms. Because it's a count of your physical matter, your mass stays the same whether you're in your kitchen or floating in deep space. We can see this in action with this photograph from the moon. This astronaut is carrying large equipment that would be incredibly difficult to lift on Earth. Their mass, the physical stuff making up their body and gear, is exactly what it was when they left home. What changed is how the environment acts on that mass. The moon has a much weaker gravitational pull than Earth. That pull is what we call weight. Weight is a force, not just a count of matter. Since the moon doesn't pull as hard, the astronaut's weight is only about 1/6 of what it is on Earth, even though their mass hasn't changed at all. In engineering, we keep these two ideas separate because we need to calculate the specific forces pushing and pulling on everything we build. To turn mass into a force we can use in a design, we use a simple calculation. Weight equals mass times the acceleration of gravity. For a 70-kilogram student on Earth, we multiply that mass by Earth's gravity, which is 9.8 meters per second squared. The result is 686 newtons. In the world of engineering, that is your actual weight. Now, imagine that force isn't just a pull, but a push against a surface. When you spread a force in newtons across a specific area, you create pressure. We measure this in pascals. 1 Pascal is defined as exactly 1 Newton of force spread out over 1 square meter of area. However, the Pascal is a very small measurement. To give you an idea, a single feather resting on a table creates about 1 Pascal of pressure. Because of this, using pascals to calculate the strength of things like steel or concrete would lead to inconveniently large numbers. To keep our calculations manageable when designing large structures, we use larger units. This is where the megapascal, or MPa, comes in. As you can see in this textbook excerpt, mega represents 10 to the power of 6. That means 1 megapascal is equal to 1 million pascals. You'll find MPa used throughout engineering textbooks to describe the strength of materials. But there is a practical hurdle. Engineers rarely draw blueprints in square meters. Most of the things we build, like machine parts or steel bolts, are measured in square millimeters. This creates a challenge for students. You have material strengths given in megapascals, which are based on meters, but the parts you are designing are measured in millimeters. We can bridge that gap by following the math on this page. It shows the steps to convert a force on a square meter down to a square millimeter. The final result shows 1 Pascal equals 1 millionth of a Newton per square millimeter. Now, remember that mega also deals with a factor of 1 million. Because these two values, the mega and the square millimeters, both involve a factor of 1 million in opposite ways, they cancel each other out. This means 1 megapascal is exactly equal to 1 Newton per square millimeter. This relationship is incredibly practical. It means you can take a material strength from a textbook and apply it directly to your millimeter scale drawings without any conversion math at all. Let's test this with a problem. Suppose a 50-kilogram steel block rests on a square plate that is 100 millimeters wide. To find the pressure, we first need the force. We convert the mass to weight by multiplying 50 kilograms by Earth's gravity, 9.81. That gives us a force of 490.5 newtons. Next, the area of our square plate is 100 times 100, which is 10,000 square millimeters. If we divide our force by that area, the pressure is 0.049 newtons per square millimeter. Now, if you need that answer in megapascals, the relationship we found earlier tells us the number stays exactly the same. The answer is simply 0.049 megapascals. Here is a quick check for you. If a material has a strength of 500 newtons per square millimeter, what is that value in megapascals? Tell me in the comments. By keeping mass and weight separate and understanding how these units relate, you've cleared one of the biggest hurdles for new students. Tamani Metnat Ranglovshe, your hard work will pay off. See you in the next one.